Welcome back to our machine design series. This is the third and final video on shaft design, and today we're really focused on components that we couple to the shafts. So first of all, let's start with a couple definitions. So torque is transmitted from a shaft to a hub by mechanisms such as keys, splines, press fits or interference fits, okay, and let's have a little drawing here of our shaft. And this shaft needs to fit inside of the hub of some component. Could be a gear, could be a pulley, could be a flywheel. Well, I don't need that arrow. Okay, so here's our hub of whatever component. So let's go ahead and define hub. It's a central component of a rotating element. So again, that might be a wheel, a gear, a pulley. And in this section, we're going to talk about different ways that we can connect a hub to a shaft. So first, let's start off with keys. So a key is used to transmit torque between a shaft and a shaft supported element. Okay, so let me attempt to draw a key. So here's our shaft, and into the shaft a key seat will be cut. Okay, so let's label the shaft. This is the key seat. Okay, and the key itself, there's many different shapes and styles. I'd encourage you to go take a look at some of them on McMaster-Carr, for example. But here we'll just draw a square key or a straight key. It's most commonly used type. And then, so the key fits inside of the key seat, and then that can then be inserted into the hub, which has a keyway. Okay, so technically the key seat is milled into the shaft and the keyway is in the hub. Sometimes you'll hear people use those terms interchangeably. That's okay, but I'm gonna, teach you the technically correct way from your textbook. Okay, and the inner diameter hole inside of the hub is commonly called the bore. All right, so when we're designing a keyed shaft, we have to consider stress concentration factors. So when designing keyed shaft, stress concentration factors, which remember we denote those with capital K sub T, should be considered. Oh, and I just realized I made a heading for myself down here for keys that looks a little bit nicer, so let's move all of this down there. Okay, so let's talk about a couple different types or shapes of key seats that have different stress concentration factors. So first, an end milled key seat. This is probably the easiest type to manufacture. So here's what it looks like from above. Sort of a rounded end, rectangular shape. And then from the side, has these straight edges to it. Well, that's as good as it's going to get. Okay, and so the way that this is milled is we take our bit and we drill straight down. We let it run straight across, and then we pull it straight back out, right? That's how we get this shape when we're manufacturing this type of key seat. Okay, now let's talk about a sled runner. Key seat. Okay, so this one from directly above has more of a rectangular shape or appearance. But then from the side, we have a more gradual change from one geometry to another. So the way that this would be milled is we would have our drill bit here, we would gradually lower it as we move along the piece, then we let it stay flat for a little bit, and then we gradually raise it back up. So this is a little bit more of a complicated milling operation, and so that means that it's a little bit more expensive to manufacture. But if we look at the stress concentration factors in bending for each of these, the end milled key seat has a stress concentration factor of 2.14, and the sled runner key seat has a stress concentration factor, again in bending, of 1.7. Okay, so that's a 20% difference maybe between the two. Is fairly significant. And so if your design is, if you are finding that you have too high of a stress concentration at one of the edges of your key seat, it may be worth moving from something with these sharper edges to something like a sled runner with more rounded edges. Again, that's going to increase your manufacturing cost, and so that needs to be weighed against the gains that you'll make by reducing stresses in that location. Of course, we're primarily concerned with safety as engineers. And you can also take a look at your textbook, table 7-1 in Shigley, to find other stress concentration factors, including the stress concentration factor for end milled key seats in axial and shear loading, and sled runner key seats and those other types of loading, as well as other shapes of key seats with their stress concentration factors. Okay, so now let's talk about tolerancing keys. So parallel keys may be positively or negatively toleranced. If negatively toleranced, the key will never be larger than the nominal size. So for a negatively toleranced key, you can cut with a standard milling cutter to the nominal size and then cut it down from there, and the key will fit inside of the key seat with a slight clearance. If positively toleranced, the key will be slightly larger than nominal size. Okay, so you may want to use positively toleranced key when you need a closer fit between the key and the key seat, but this will or could require additional machining of the key. So it's probably going to be more expensive to have a positively toleranced key. One of the reasons you may want a positively toleranced key is because of the issue of backlash. So backlash may occur when the loading torque changes direction. When that happens, any clearance between the key and the key seat can result in high impact and high stresses. So if we take a look at what this might look like if we have a key in here. Okay, so here's my shaft. If my key is smaller than the key seat, when this thing rotates, and the shaft is going to want to go one direction and the hub is going to react to that, go the other direction, or vice versa, then because there's a little bit of clearance here, or really clearance here, we can have impact between these two pieces. And same thing on this side. This little bit of clearance will get taken up when it starts to move, and we'll have impact between those two parts there. And that impact can lead to damage of the key and the key seat and the keyway, especially over a longer period of time. Okay, so some ways to avoid backlash. We can use a positively toleranced key. And keep in mind that if you use a positively toleranced key, yes, that is going to fit better into your key seat and your keyway. It doesn't necessarily mean that you're going to have no backlash, okay? It means that you're going to have less clearance than a negatively toleranced key, and so you have less impact, less high stresses, but especially over time, you can still have deformation of the two parts that can build up and lead to not good situation with backlash. So it doesn't mean that you don't need to still consider backlash as a possibility if you use a positively toleranced key, just that this can help reduce the negative effects of backlash. And another option that similarly can help reduce negative effects of backlash is to use a set screw to secure a negatively toleranced key. Okay. As far as sizing a key, how do you determine how big you need to make your cross section, how long you need to make your key and your keyway and your key seat? So first of all, your key cross section is dictated by the shaft diameter. And if you want to look up specific values for standard sizes, you can take a look in Shigley table 7-6. We'll give you some standard diameter ranges and ranges for sizes of keys that correspond to those shaft diameters. And then your key length is chosen to carry the torsional load. So, generally, should not exceed 1.5 times the shaft diameter. to avoid excessive twisting. So remember when we first introduced the idea of torsion of a shaft, we drew something like this. We said, okay, before we apply any kind of load to this shaft, we have a straight line that connects these points A and B. Then we apply some torque to this thing. Okay, now this line has deformed so that this point is now B prime. So we've twisted the shaft under torsion. And if you have a key that is sitting on this shaft, then that key is also going to become twisted as the shaft twists. And if it becomes excessively twisted, then you can get issues of binding or of the key coming loose from the key seat. So either way, not a desirable outcome. So we need to limit the length of the key to avoid that. And the key length is also limited by the hub length of the attached component. Okay, so the whole point of a key is to attach a hub to a shaft. So if the key is not in contact with the hub, then it's not really achieving that goal. So it really doesn't help us in making that connection to have a key that is longer than the hub length. All right, so last thing on keys, let's talk about key failure modes. So keys typically fail in one of two ways. The first is a shear failure. And the second is a bearing failure. Make a little table, go through each of these. So, first, for shear failure. This occurs when the key is sheared across its width at the interface between the hub and the shaft. So remember that if we draw the loading on a key, maybe a square key like this, then I have a force from the hub that's going in one direction on one side, and I have a force counteracting that from the shaft on the other side. And so one way it might fail is to shear these two halves past each other, right? They're being forced in opposite directions. And we can calculate the critical stress of the key under this type of loading by taking the shear force, F, and dividing it by the area that's being sheared. So that force is going to be the applied torque to the shaft divided by the shaft radius. And the shear area is going to be the width of the key, so that's this dimension here, times the length. So that's in that drawing that's going into the screen. And this, again, this is for a rectangular key. Okay, and then we can take that critical stress and calculate a factor of safety by comparing that stress to a strength value. So comparing the shear stress to the shear yield stress or shear yield strength will give us a factor of safety guarding against yield by a shear failure mode. And if you don't have the shear yield strength, you can estimate it using 0.577 times the tensile yield strength divided by critical stress tau. Okay, so that's shear failure. The other type of failure that's common for keys is when the key is crushed due to a compressive load. Okay, so if I look at our square key cross-section here again, and I've got a force that's acting on one side here and on the other side here. One thing that can happen is the material directly underneath this force can yield in a compressive failure mode because the compressive stress from this contacting force becomes too high. Ooh, okay, so the critical stress for this failure mode is the crushing force, F, divided by the area that is being crushed. And so that force is still the same as the applied torque to the shaft divided by the radius of the shaft. And now the area that's being crushed is half the height of the key, so the height is this dimension. So half the height times the length. And again, that's for a rectangular key. All right, and then for our factor of safety, we can compare this normal stress to the material's compressive yield strength to get a safety factor guarding against compressive yield. Okay, and so to assess the overall safety factor of a key, you're going to need to evaluate both failure modes, safety factors for both failure modes, determine which safety factor is lower, and that is going to be your safety factor that or the failure mode that dominates this design. So if I find that my safety factor guarding against shear failure is lower than my safety factor guarding against bearing failure, then that means I find that shear failure is more likely to be the failure mode of that key, and that lower safety factor becomes the overall safety factor of that component. So finally, we've talked about keys. Now let's talk about splines. So splines are another method for attaching hubs to shafts. Let's define it first. Splines are formed by contouring the outside of a shaft and the inside of a hub. All right, and splines have a few advantages over keys. So first of all, splines can transmit larger loads. Splines can accommodate large axial motions. And then all other factors being equal, meaning we're making this out of the same material, we have same strength and stiffness properties, splined connections have a longer fatigue life than keyed connections. And that's because the loads get more evenly distributed. And lastly, one drawback of splines is that the manufacturing cost for splines is typically higher. Okay, so that's a lot of text about splines, and I still haven't shown you what they actually look like. So let's try to draw it. There's a few different shapes. First, let's go with the straight spline, and this looks the most like a keyed connection. So if I draw my hub, then a straight spline has sort of many keyways carved into it. sort of color in the rest of this so that you know that this is the hub. Okay, rough drawing, but there it is. Next, there's a serrated spline. Okay, so again, I'm going to draw my hub. And this, I think, looks kind of like a sun or a star. We have these equally spaced teeth with an included angle. And this is mainly used for smaller diameter drives. And that the reason for that is because we can fit a lot of teeth on a small circumference when we have this serrated shape. Okay, and finally, the involute spline. We haven't talked yet about what an involute is. The shape of an involute is something very specific that we'll talk about when we get to gear teeth. But for now, all that really need to know for this shape is that it's sort of like the straight spline, but with these rounded edges that I am really struggling to draw. I gotta redo that. Okay, I'll live with it. Anyway, it's meant to look just like the straight spline, but with more rounded edges. And that smooth transition between the teeth lowers stress concentration, so this increases the fatigue properties. Okay, and the straight spline, when we take a look at it, you can see that this looks just like a keyway for a straight key, but instead of just one, we've got many spaced around the circumference, and you can do as many as you like, depending on your design. And so that right away, looking at those shapes, you can see why these advantages exist, right? The splines can transmit larger loads than keys because effectively, as this is drawn, we have 1, 2, 3, 4, 5, 6 keys that are splitting that same load that a single key would be carrying. So we can transmit larger loads, we can accommodate larger axial motions. This is essentially because the spline and the splined shaft and the splined hub are two parts that can now slide axially against one another, and we're not worried about another part, being the key, slipping out as they translate axially against each other. The spline will still be there, and we can put stops on the outside of the hub or on the outside of the shaft to limit the ends of that axial translation, but we still just have two parts to worry about rather than three. And then all other factors being equal, splined connections have a longer fatigue life. Again, that's related to the fact that we can just accommodate larger loads. We have a way to split loads between multiple different keys or different teeth on the spline. But of course, the manufacturing cost for spline connections is higher. We have to machine out 6 keyways to make this part rather than a single one to make a keyed hub like we had drawn up here. Okay, so that is the end of this video for coupling hubs to shafts. We talked about keys and splines. We didn't get to press fits. I may put out another video on that, but we won't talk about it in class since you guys cover that in a different course at the university where I teach. So anyway, I hope you liked the video, and in the next one we'll start talking about mechanical springs. So thanks for watching. See you in the next one.